Okay, so I need to show you what I promised to show you is when I take a patch of membrane, representing it as a small spherical cell, which I will call soon isopotential sphere, meaning that there is no change in voltage across this membrane, so there will be the voltage difference between the inside and the outside will be V at any location, so this will be isopotential, no change, no drop in voltage across this membrane. It will be an isopotential cell. I showed you that when I inject current here, I get voltage response V that looks like this. This will be my I, this will be my V. And I told you that the representation of this as a first approximation is an RC circuit like this. This will be my inside, this will be my R, this will be my C, this will be out. So why do I say that a good electrical circuit representing this behavior of a cell is an RC circuit? And this is because of the mathematics of this circuit. And I can write down the equation that describes what happens when I inject current to the two sides of this circuit I, as I did before. What will be the voltage development between these two sides, V? So I want to measure V in response to I. So V is the voltage difference between outside and inside, and I is the injected current, and I can write the following basic equation. I'm saying that the total current that I inject, the total current that I inject into this location can either go and become a capacitive current or can go and become a resistive current, because according to Kirchhoff's law, everything that is injected here must split either in this branch or in this branch. So that's exactly what I'm writing now. I'm saying that the capacitive current, which is C dV dt, this will be my capacitive current, plus the resistive current, which is just regular Ohm's law, V divided by R, must equal I, the injected current. So this is my resistive current, this is my injected current, So what I wrote here actually is Kirchhoff's law, saying that the current that I inject splits into capacitive current here, charging the capacitance, and this, the resistive current, is the current that goes through the resistance and leaks out. Actually, current can only flow outside through the resistance, and it can charge the capacitance. If I inject a positive current, then the capacitance is charged inside. It's charged inside the cell. Inside the cell, you charge the capacitance with positive charges. So the inside of the cell becomes positive, and that's what you see here. The inside of the cell becomes positive, and that's our agreement, that if I inject a positive current inside the cell, I get a positive voltage inside the cell, which I call depolarizing. Okay, so now I have to take this equation and show you that when I solve this equation for V, I get such a behavior. So let's see. So I'm trying now to solve this. And this is actually very easy, because now you have a very simple linear, because this is constant, the capacitance. This is constant, the resistance. There is a constant current I. It's a linear, one-dimensional partial equation. So you only have dV dt. There is only time here. T is time. As I said before, this is now, here I inject it in time. So C dV dt plus V divided by R is equal I. And I need to solve this equation. It's a very simple solution. So let me write to you the solution. But before writing a solution for such a thing, I have to define initial conditions. What do you start with? So we already said that we start with V at t equals 0 equal, let's call it 0. So I start with V equals 0 here, V equals 0, and I get to some V with time. So I want to solve for V, I want to solve this equation for V as a function of time. So the solution looks like this. V as a function of time is equal I, which is my current injection, multiplied by R, which is the resistance, multiplied by 1 minus E exponent to the power of minus t time divided by R multiplied by C. This is the general solution for this equation, assuming that V at t equals 0 is indeed 0. So let's check it. Let's say that t is equal to 0. What happens then? When t is equal to 0, e to the power of 0 is 1. 1 minus 1 is 0. So V at t equals 0 is 0. So this means that we satisfied our initial condition. That's fine. Let's look at the other extreme, which is the case when I inject my current for a long, long time, for an infinite time. So I inject my current for a long, long, long time. What happens then? So if t goes to infinity, e to the power of minus t goes to 0. This goes to 0. And you are left with V at t equal infinity is equal IR. Because this goes to 0, and you have in IR. Okay, so these are the two extreme cases. You start with V equals 0, and if you inject this I current for infinite long time, you will get at the steady state. This means steady state because you inject so long and the voltage remains at its steady state, and the steady state value is I multiplied by R. So that means, again, I'm repeating this drawing. I inject current I look at voltage V of t. Okay, at 0, here at time 0, I have voltage 0. And at infinite time, if I inject it very, very long time, this becomes I equal to I multiplied by R. So this is the steady state value of this voltage development if I wait enough time. And this comes from this equation.